Welcome back to London Maths Outreach. This week we'll be doing the second installation in the series, Mathematical Aspects of Computer Science. And we're going to be talking about arithmetic and how to do arithmetic using circuits. If you recall, last week we introduced logic gates, which form the basic building blocks of computer circuitry. And this week we are going to focus on a specific application of them, in particular how to make digital circuits that allow a computer to add, subtract, multiply, and divide. We're not going to focus so much on division, but we will say something about addition, subtraction, and multiplication. So to do this, we first need to talk about the binary number system. Computers are not used to using our number system, which is the base 10 system. Instead, they use the base 2 system, or in other words, the binary number system. And although I'm aware that some of you may have seen this before, either in school or in some other kind of outreach capacity, maybe even in another London Maths Outreach course, I wanted to start over and give an introduction to the binary numbers. I think it's important to see them from the beginning and to see how to motivate them, and in particular why they're useful in the context of computers. So we are used to using the base 10 system. So let's think about what this means. And let's do this via an example. So consider the number 3,478. This number is some string of digits, and it's meant to represent some quantity. In this case, a very big quantity. But if you think about it, this string of digits is really a kind of code that encodes the quantity, and we can know how to read this number if we know how to decode this code. So what does this code mean? There are 4 place values in this particular number. The first is called the ones place, the second is called the tens place, the third is called the hundreds place, and the fourth is called the thousands place. And as you can see from this expression, these correspond to powers of the number 10. So if you want to decode this string and create some quantity, first you have to add 8 times 10 to the 0. So the contribution of 8 to this quantity is via the 0 power of 10. Then you have to take the number 7, which is in the tens place, so its contribution is 7 times 10 to the 1, which is 10. 4 is in the hundreds place, so its contribution is 400, which is 4 times 10 squared. And lastly, 3 is in the thousands place, so 3 contributes 3,000. So we started with some arbitrary sequence of numbers. And we know how to decode this because we know that we work in a base 10 system, where each place value corresponds to a power of 10. Okay, so as I said, each digit represents a different place value. One important feature of this system, which is extremely crucial in the way that we use it, is that expressions like this are unique. In other words, the quantity 3,478, which is represented in this base 10 system by this string of numbers, cannot be represented by any other string of numbers. Except, of course, if you add zeros on the left-hand side. But we'll ignore that. So let's make this mathematically precise. This may look a bit complicated, but I'll break it down. What I'm saying when I say that expressions like this are unique is that if I take 2 numbers, so call one of them D and call the other one E, and if I write them in terms of their digits, so assume that D is a number with n digits and E is a number with m digits. And when I say number, I mean positive whole number. So I can write these numbers D and E in terms of their digits as follows. So Dn comes first, then Dn minus 1, Dn minus 2, all the way to D0. And on the right-hand side, Em comes first, all the way to E0. As I said before, I'll assume that the leading term is not 0, because otherwise I can just get rid of it and this doesn't change the number. Then if I take 2 of these numbers, they're equal to each other if and only if, first of all, the length of these numbers are the same. So n is equal to m. This means that D and E both have the same number of digits. And secondly, if these 2 numbers are equal, that means that each of these digits have to be equal on both sides. In other words, Di is equal to Ei for I ranging from 0 all the way to n. So this is a really important feature of our number system because it means that we can't write down 2 different expressions which look different but actually represent the same thing, because that would be confusing. So as I said, this is the base 10 system, and this is the system that we are used to using in our everyday lives. I mean, this is the system that you learn when you're a child, and you use to count and you use basically for the rest of your life whenever you need to count something. But there's no particular reason that we had to choose this number 10. This number 10 is completely arbitrary in some sense. Historically, probably the reason why we use the number 10 is that we have 10 fingers. So it's convenient to sort of count on your fingers from 1 to 10. But what we can do is just replace the number of 10 with any whole number b, which is greater than 1. So we can take the base 10 system and we can try to rework it so into a base b system for some arbitrary number b by applying the same principles and see if we get something that still works. So b could be any number greater than 1, which is a whole number. It could be 2, it could be 3, 5, 6, 15, whatever you want. Let's talk about this base b system in more detail. Like before, I have some kind of rule where I take a string of digits, so dn going to d0, and I write them in terms of powers of b, which determines the quantity that they represent, or that this particular string represents. So this is some arbitrary sequence of digits, dn all the way to d0. And it means something similar to what we meant in the base 10 system, but now we've replaced 10 with b. So d0, which is in the ones place, now represents d0 times b to the 0. d1, which is in the b place, represents d1 times b to the 1, all the way up to dn times b to the n. So this is exactly the same as in the base 10 system, except now b can be any other number. For instance, if b is 4, then this would be d0 times 1 plus d1 times 4 plus d2 times 16, etc. Now, one important thing which I didn't mention in the base 10 system, but is extremely important to take note of, is that the digits that I'm allowed to put into these expressions are only allowed to be in between 0 and b, and have to be strictly smaller than b. In the base 10 system, if you just replace b with 10 here, that means that the digits range from 0 to 9. And this is exactly what you will be familiar with if you just write down a number in base 10. The digits that you use to represent this number have to live from 0 to 9. There is no other digits possible. But now if you change the base and replace it with something like 2 or 3 or 4, etc., then the number of digits that you're allowed also changes. So in particular, for, let's say, a base 4 system, the digits I would be allowed are 0, 1, 2, and 3. So there's 4 digits allowed in a base 4 system, and they range from 0 to 4 minus 1. And the same thing is true for any p. So in a base b system, you have b digits. Just like in a base 10 system, we have 10 digits, 0 through 9. If you write expressions like this, and they're meant to signify these kind of expressions, then, again, these expressions are unique. This means that if I take any positive whole number, there's only one way to write it as a string of digits in the base b system if I assume that the first digit is not 0. And this is an exercise that I'll put after the video to make this precise and prove that this is actually the case. And as I said, we call this the base b system. Now, computers, as we discussed last week, they operate with wires, and these wires you can think of as either on or off. They carry either a high voltage or a low voltage. Because of that, it's useful to have a system which has 2 possible states. Now, if we look on the previous slide, I said that the digits that appear in these binary numbers have to be in between, strictly in between 0 and b. This means that if I put b is equal to 2, then the numbers I'm allowed are either 0 or 1. There's only 2 digits that I'm allowed in the binary system. And this is very convenient for a computer, because a computer represents the 2 states 0 and 1 very effectively using high and low voltages on the wires. So if we take the expression for an arbitrary number in the base b system, and we replace b with 2, then this is what an arbitrary string of digits is going to look like in the base 2 system. But now, as I said, these di's are either going to be 0 or they're going to be 1. So in this long string of digits, I just have zeros and ones. And these represent numbers. So let's try to work this out. Let's try to see what binary numbers actually look like. Here I've made a table of all of the binary numbers, representations of the base 10 numbers 0 through 23. Okay, let's start with 0. So 0 is equal to 0 in binary. 1 is equal to 1 in binary. But suddenly, if you want to express the number 2 in base 10 in base 2, then you have to convert somehow. And the problem is that you don't have any more digits. I mean, 0 and 1 have already been used. So now I have to use some combination of 0 and 1 to express the number 2. But if you remember what the base system means, this first place is the ones place, and the second place in this system is the twos place. Before it was the tens place, but now it's the twos place. So this number actually represents 2 because it's 2 times 1 plus 1 times 0. Okay, now we can try to do the number 3. In this case, we have 1 and 1. Again, this is the twos place and this is the ones place. So 1 times 2 plus 1 times 1 is just 2 plus 1, which is 3. So this works sort of similarly for all these different numbers. We can do one more example, which is 18, just for the purposes of illustration. So 18 in binary is represented by the number 1, 0, 0, 1, 0. If you break this number down, there's a ones place, a twos place, a fours place, an eights place, and a 16s place. In this case, I'm taking the number 16, which is appearing in this binary number, and the number 2, and I'm adding them together. So 16 plus 2 is equal to 18. Right? This is 16 times 1 plus 2 times 1, which is equal to 18, and I'm ignoring all the other places because there's a 0 there. So these other places don't actually contribute to this number that I'm trying to represent. So I would encourage you to take a look at this table, work out some examples on your own, and try to make this make sense in your head. And one nice thing to do as a practice exercise, which I'll give you some exercises for in the page after the video, is to just take a number in base 10 and convert it to base 2. And vice versa, take a number in base 2, which you can just sort of write down as an arbitrary string of zeros and ones, and try to write down what its equivalent number in base 10 is. This is a good exercise to get some practice with this number system. So once you have this number system, you can try to do arithmetic like you're used to in base 10. So in particular, when we have two numbers in base 10, one thing that we frequently do is add them together. And we could do the same thing with numbers in base 2. And if you're used to doing addition on pen and paper, you can do the same kind of technique with binary numbers, and the rules are roughly the same. So just so I can illustrate how this works, let's go through an example. So let's add the number 10110 to 10101. 10110 is a number in base 2, which represents some number in base 10. And if you look at the place values, this is the 16s place, this is the 4s place, and this is the 2s place. So 16 plus 4 plus 2 is 22. This number is also a binary number, and it represents the number 16 plus 4 plus 1. So this number is 21. So I'm taking 22 and I'm adding it to 21, and I want to get the result. But instead of doing that, let's try to do this just staying in the world of base 2. So to add, we just do the usual thing. First you look at the ones place and you add these two numbers together. So 0 plus 1 is equal to 1. Okay, I move over. 1 plus 0 is equal to 1. Okay, now I move over again, but now I have 1 plus 1. Now instinctively in base 10, I would be tempted to write 2 here. But I can't write 2 here because I'm in base 2, and I don't have the number 2 available to me. The digit 2, rather. So instead what I do is, I look at what this sum actually is. It's the number 2, but in binary this is written 1, 0. So really the sum is 0, and then I carry the 1. So every time you add 1 to 1, you get a 0 down below, and then you have to carry the 1. And this really corresponds to adding the number 2. Okay, now I can add the next column. So 1, 0, 0 gives me 1. And finally, 1 plus 1 is again 1, 0. So I just put in a 1, 0 in the end. And you can check for yourself that this number, which is in the 32nd place, plus this number, which is in the 8th place, plus this number in the 2's place, and this number in the 1 place, add together to give you 22 plus 21, which is 43. Okay, so in base 10, we just computed this sum. 22 plus 21 is equal to 43, and you should check that this number is actually 43. Okay, so now it's your turn. Take a look in the exercises below to get a bit more practice with binary numbers and adding binary numbers. And afterwards, we'll return and discuss a bit more about binary arithmetic.